Okay, today is April 1st, 2025. We will start the topic of fluids, no? Mechanical fluids. Mechanical fluids is huge, huge. We cannot cover everything because, of course, we will not see, for example, the Navier-Stokes equation. We will not see the Newton law of friction between water and the layers of water between each other and the walls. For example, when the water moves in a tube, you should know that the surface of the tube has zero velocity of water, but in the center is maximum. There is a gradient of velocity. These kind of things we will not see it here, but we will see a few basic things. Instead, as everything in a science, everything is huge, vast. So we cannot, but at least you can have a naive notion, especially you guys, you do marine science, no? You study fishes and so on. So it's important for you to understand these things. So let's start with buoyant force. When I say buoyant force, what do you understand? It's the force for what? Exactly. When you are sinking in the water, you feel yourself. How do you feel yourself when you are in the water? Depends if I have air in my lungs. Exactly. Well, the tendency is to become, yeah, like you are not that heavy, no? You can carry anybody in the water. And what's the reason? Because the buoyant force is helping you. It's helping you. The buoyant force help our ships to float on the over the water. Because of course the ship is designed with lower density than the water. Then you will say, but the iron has larger density than the water. No, but the total design of the ship, it has some cameras full of air, just like humans when we fill our lungs with air, or even the fishes manipulate the amount of gas they have inside in order to go up or lower. So they apply physics, but they don't know they apply physics, actually, the fishes. So if you see this picture here, I hope in the camera can catch because sometimes the light, the contrast of light. You see this column of water here. Well, there is a pressure here in this level. And when we see hydrostatic, we will see that the pressure at this level is larger. So there is a difference between the force pointing upper is larger than the force pointing lower. So that's part of what we will call buoyant force. Buoyant force, as you can see, when you are swimming in the water, you have your weight, but you also have the buoyant force helping you to float. And actually, you will float naturally. If you relax in the water, you will float. But if you start to shout and do many things, as many people do, probably including myself, then of course you will sink. I mean, when you don't know how to swim, you panic and you start to do many things and sink. This is how people die. But if you relax, the tendency is you will float. So something, and you should know that the buoyant force can be calculated. It's equal to what? Somebody saw this in the school, in the primary, high school, or it's equal to the weight of the fluid you displaced. For example, that's why these guys made the shadow here. Can you see the shadow they made here? Because this volume, well, using the density of water, density of the water times this volume gives you the effective mass. Okay. Then, of course, it's the weight of this fluid which is displaced. So the more you displace fluid, the larger is the buoyant force. So it means a person bigger receive larger buoyant force than a person who is not that big. Okay? So the ships, later we will see how to calculate these things. Don't worry so much about this, but there are ways to calculate the fractions in mass of an object. Look at the ships. The ships are constructed by iron. Why did Titanic sank? Because it was metal. It was from metallic, no, iron or something, some metal. Of course, the metal has larger density than water, and if your density is larger than water, you will sink. Remember, low density tends to float, high density tends to go down. The air has lower density than the water. That's why, etc. When the air is heat, what happens? It expands, density is lower, and then it goes up. Exactly. With the water is the same. There are currents of waters for difference of heat. The bottom of the ocean is much colder than the surface. So there is this permanent circulation of water, which generate partial currents. The other portion of the currents is the wind, hurricanes, tornadoes, whatever, etc. But look at this ship. The ship can float, and the Titanic could float before the accident. No. Now, what was the reason? Even if it's metallic, the total shape inside has empty space, so the total density of the ship is lower than the water, even if it's metallic itself. The cameras are full of air, etc. These things can be calculated, certainly. These problems, don't worry so much about it right now. This is a possible experiment you could do. For example, you put this balanza, we call this balanza in Spanish, and you put a weight here, and you put another weight here, but with water. Evidently, the buoyant force here will make mind that originally these two guys have the same weight, but here the buoyant force helped to go up a little bit, so you have to decrease the weight. Otherwise, they will lose the equilibrium, and there will be a torque. No? Now, when an object is near the surface, there is a portion of the object over the surface of the water, and there is a portion inside the surface of the water. And this is exactly the kind of problems we will do, because these are interesting and are a little bit more complicated, because of course, if you have the whole body inside, you already know the volume which is displaced. No? If I sink this ball completely inside the water, I know that the total volume displaced is the volume of the ball. Easy. But when it's partially immersed, then only a portion of the volume is immersed. But I should be able to calculate that. Then let's analyze this a little bit in detail. We have this object is in equilibrium, so gravity is going down, the buoyant force is going up, and if it's in equilibrium, the summatory of forces is equal to 0. Then, of course, gravity, let's put mass of the object times gravity is the weight. It has to be equal to the buoyant force. Let's call it B. But the buoyant force is the weight of the displaced fluid. So it should be some mass times gravity also. Then let's put the gravity here, which will cancel with this. What will be that mass? It will be the density of the fluid times the volume displaced, V sub D. Density times volume is mass, right? You saw that in the school. Then, of course, I could calculate the volume displaced as the mass of the object divided by the density of the fluid, in this case, water. There is an ocean or a river where people can float easily. Which one is that? Is that sea, I think? El Mar Muerto. Perhaps. It's very salty, right? Then what happens if it's too salty? Much larger density, so in comparison, it's like equivalent. If we apply, let's call it relativity, our density is smaller, no? Compared with our water. And then we can flow easily. Huh? You will be happy. You don't need any this kind of life, what do you call these things? Life guards? Life jacket. The jacket we use when in the hypothetical case, the airplane falls. Well, I don't want to talk about that, but especially when you are going to travel. Well, let's say, let's say when you are swimming for joy, and some people don't know how to swim, and they use this kind of devices full of air, no? Of course, if it's full of air, it will have the buoyant force will be effective there because it's a low density. The air has much lower density than the water. Then this is the way how you calculate the displaced volume below the water. You can apply the same to the iceberg. Later, I will find the problem of the iceberg. I think after the break, I will do it because the review of thermodynamics took a little. But this is a simple analysis. Now, what happens? What happens if for any reason I sink the whole object? I put this ball here. Let's assume that the density is low enough for being on the surface, but by purpose, I just put it down and I release it. What will happen? It will go up. It will accelerate. Why? Because it's not equilibrium anymore. But still the same forces apply. But there is one additional force, which I will count is the friction with the water. No? Well, let's put the forces here. It will be the weight. It will be the buoyant force. And the buoyant force in this case will be the density of the water, the volume of the ball, because the volume of the ball is the displaced, is below the water. So it's displaced, that's the amount of fluid it's displacing. The amount of volume is displacing is the volume of the ball itself, times gravity. And of course, it starts to move upward. Is this equal to mass times acceleration, which is vertical. Let's put so y. And in addition, if you want to be more rigorous, you will include the friction between the water and the ball, which go down. Well, let's assume that you neglect that friction because we want to simplify that part. Then this is the total amount of forces. Then you will have weight minus rho of water, volume of the ball, gravity, equal, since I took the positive as down was positive, upward as negative, this will be mass, acceleration, and this volume is 435, the radius of the ball to the cube. Is the volume of a ball, a sphere, right? If I throw a coin to the water, what will happen? It will sink. Why? It's metal, high density, it will sink. Exactly, but still it will feel buoyant force. So it's not the same throwing a coin to the window here than throwing a coin to the water. It will take longer time to reach the bottom on the water because the buoyant force is stopping beside the friction. No? In addition, there is a friction against the motion of the ball. So exercise, I want you to calculate, I want you to think because this is about thinking. In advance, before finding the problem of the iceberg, I want you to think you are in the ocean. You see an iceberg here. Iceberg. Let's assume you are Leonardo DiCaprio in the movie. And then you see the iceberg and you shout. Well, he's not the one who shouted, actually, somebody else. But you see iceberg, iceberg. Okay, this is the iceberg. The iceberg is monumentally big, but it's much bigger below the water. And this is what I want to calculate right now. Let's calculate. So for that purpose, can you find the density of, you need, which information do you need in advance? For knowing that. Of course, it depends, but let's put the forces here. You have the weight of the iceberg. You have the buoyant force, and they are supposed to be in equilibrium. And the buoyant force is equal to the weight of the displaced fluid here. Yes, at the end, the equation for the iceberg, for finding the fraction of iceberg sank, is like this: is mass of iceberg, gravity equal to density of the water, no density of the ice. Actually, let's do it better here. This is density of ice, volume of ice, because that's the mass. And that counts all the iceberg from the bottom to the top, completely. But this density of this side of the buoyant force, it counts only the displaced fluid, which is this volume here, the volume below the water. Because we have said that the buoyant force is the weight of the displaced fluid times gravity. So gravity doesn't play any role in this calculation. You don't even need to know the value of gravity. It's independent of that. So displaced volume, and you have the volume of the ice. But the volume of the ice is the volume upper plus the volume displaced. Then let's put here density of ice, volume upper plus volume displaced equal density of water, volume displaced. And then we can start to play. I could divide here. I could say volume upper plus volume displaced divided volume displaced equal density of water, density of ice. And then this will give me blue background is too strong, so let's restart this. This will give me upper displaced plus 1 So what is the fraction sink here? The fraction of iceberg sank, which sank. I can solve here. Volume upper, volume displaced equal -1. And this quantity give me that fraction. I can get it from here. So I only need to know the density of the water and the density of the ice for calculating that fraction. Then now is 4:30. We go to break, and after the break, we will solve a problem using this formula. Of course, you don't have to memorize. You can see that this is not about memorizing. It's logic. It's mere logic. It's equilibrium of forces. On the left-hand side, the weight of the iceberg. The mass of the iceberg is density of the ice times the volume of the iceberg times gravity. On the right-hand side, the buoyant force, density of the water, the volume which the iceberg displays times gravity. Gravity cancels, and then I just have to add the fact that the total volume of the iceberg is the volume of the upper plus the volume displaced. Or you could even do it in this side, you could have replaced B ice minus B upper and play in that way, also in the opposite way. But with this quantity, you can calculate this, you can calculate everything. Then you will know the fraction of iceberg sank. Then let's do that with realistic numbers, with real numbers after the break, and you will see, you will be surprised about the percentage of iceberg which is below the water. Then you will understand why the Titanic was so worried when they saw the iceberg, and they tried to avoid it. Not even the biggest ship can challenge a big iceberg coming to you. Of course, these guys underestimated the danger. You remember it's not because of the movie, it's the history itself. Is they wanted to arrive faster to New York. I think they were going to New York, not from London. And then they underestimated the danger. They put full vapor full machine, thermodynamics, they apply thermodynamics. And then my surprise is that by the time they have the engines for doing reverse, no, you could see, I think that part has to be real. No, they stop the machines, they decrease the pressure of the valve, of the valves or valvulas. Sometimes I forget the technical words, but they could make the reverse engine. No? I think it's belts. No, the right pronunciation is belts. Anyway, let's stop here. Stop recording.